So let me do now the one or two problems about the motion. So the particle moves with the given velocity. And now I would consider the motion in a plane. So particle is not moving along the line like in the homework problem, but on a plane. If a particle moves on a plane, velocity is going to be a vector. So I have to specify now a vector. Now a vector in a plane has two coordinates, and each of those is going to be dependent on t. So I'll choose some random numbers here, 2t squared and t minus 5. So velocity is given as a vector, and now we have to find the displacement. Over the time interval from 0 to 10. So let me now do this problem with the check first. So if I pretend that I don't know that the integral is useful, so how would I check that integration can be useful for the problem? There are two things to check: additivity and differentiability. And of course, to check any of that, I have to specify the parameter. Well, the choice of parameter is kind of suggested in the problem. Right? So the parameter is time, and that time changes within the interval from 0 to 10. The function that I want is the displacement. Let me denote it by f of t. Now, what kind of function is that? What is f of t? As I have a motion in a plane, what is the displacement? A function of time, yes. Is it a number?
Yes. No.
No. What is it? Is it a vector? If I go like this, what is the displacement?
Starting to end.
It is from the starting point to the end point, and it's not about the distance only. It is about direction as well. So displacement is a vector. Right? So we have to understand from the very beginning, f of t is going to be a vector. Let me use f1 as x coordinate, f2 as y coordinate. And now f1 and f2 are functions of t. And now what I have is the vector valued function of the parameter t. And for this function, I have to check these two properties. Do I have additivity? And what does it mean? if I take my time interval and I subdivide it into subintervals, will I have the displacement over f of 10 equal to the sum of displacements? So what happens if I subdivide the time interval? I will subdivide my path as I travel into pieces, and my displacements over the first interval is going to be a vector from the beginning to the end point of the first part of the travel, right? Then the second vector from the beginning to the end of the second interval on the plane, and so on. And the additivity question is asking whether sum of all these, in this case 5 vectors, equal to the vector from the beginning to the very end. Well, it does. And the reason is the rule of how we add vectors. Right? That's exactly how we add vectors. So, yes, additivity holds. And the reason is very geometric. And it's about vectors. So, yes, because of additivity of vectors. Now, what about differentiability? So, this is additivity checked. What about differentiability? What does it mean in this particular context? We give ourselves short interval delta t, and we look at the motion during that short interval delta t. And then during that motion, we look at the displacement and we divide it by delta t. Does it even make sense? Because we are not dividing numbers. Right? The denominator is a number, but numerator is not. It's a vector. So we divide a vector by a number. Why should we expect this fraction to be something as we let delta t go to 0? And what is it that it becomes? What is it that it is approximately equal to? We'll be getting a vector. So it is approximately equal to a vector. Just one vector, a constant vector. What kind of vector is that? We take this displacement, divide by a number, and it becomes longer or shorter, right? And if I divide by a small number, it becomes longer. And then I take shorter interval of time, I take displacement, I divide by a smaller number, and that becomes longer. Then I take shorter interval of time, take that shorter vector, but divide by a smaller number, so it becomes longer. So I have vector here, vector there, vector there. Should I expect this process to approach something, one vector?
But it would approach it because it's on.
Well, what can you say about the direction of the vector it will approach? Does it have a direction? Can we describe the direction? If this is my motion, I start from here, move over there. What's the limiting vector? What is its direction? Is that true? Direction of the first vector I had, first approximation is something like this, right? And then direction of the second approximation was something like that. And then direction of the third is something like this. Do you recognize the familiar process of the lines that all pass through this point, and the second point of intersection with the curve moves toward the same point, and those lines approach the tangent line. Right? So the direction of all these vectors becomes closer and closer to this direction of the tangent line. Will the magnitude approach something? Or will it become infinite? Well, you see, if it becomes infinite, that's going to be a problem. Because we are going to add that kind of numbers. As we add them together, we may run into a problem. So that better be finite. Is it finite? Well, delta t tends to 0. We have to make it go to 0. Because the whole idea at the end is to make delta t go to 0. Okay? So as delta t goes to 0, we want this to become a vector with finite length. Will it? And what kind of vector is that? Well, that's exactly velocity vector. At this point. Comes as a surprise, right? Okay, well then you tell me. Well, you all studied this concept of velocity. Right? So, what does it mean that if a particle moves, then it has certain velocity at this point? What is velocity of this particle at that point? What is that?
Displacement.
Displacement over time. So velocity at this point is displacement over time. Like which displacement? This displacement over the whole time, or instantaneous displacement over what? Instantaneous time? Oh, I'm sorry, instantaneous time is 0. There is no such thing as instantaneous time. So what is it that you do when you describe velocity at this point? How does it look like geometrically? It's a vector along the tangent line, right? Like this, isn't it? So what is it? It goes along the tangent line, so it never goes from this point to any point on that curve. the curve goes away from this tangent line immediately. So, well, that's exactly why it goes away, because of the presence of acceleration. But how to describe that vector v? Because I cannot say it's just displacement over time. So, well, if you try to describe the direction of this vector, you look at the displacement, you divide it by time, and you get a vector in that direction, right? But then you say, well, what happens over shorter time? Over shorter time, you have a different displacement, you divide, and you get a different fraction. And then you keep doing that, and the directions of these vectors approach this direction. So what is v then? Isn't it limit as what?
So it's going to be 0.
As time goes to 0. What a surprise, right? This is what you learned in calculus 1. The velocity is limit because it's derivative of what? Of position. And this is exactly what it means. And that was exactly what I was asking for. So this limit of those fractions is exactly the velocity vector. So velocity vector at the beginning. But you know, there's a problem here. I wanted this velocity vector to be one vector, because that's what I assumed somewhere there. I wanted this to be a constant, or approximately a constant. Now, velocity of my particle at this point is like that, and velocity at that point is like that. I don't see these to be almost the same. So what is it exactly that we mean there? I'm not saying that this rate is the same during that interval, right? What is it exactly that I want? Remember when we did the area problem, we looked at this short interval delta x, and we said that what we see is not a rectangle. But it's approximately a rectangle. And approximately it has a height. What is the height? Oh, it's approximately some number, right? But what do we mean by approximately some number? Because it changes. What do I mean by approximately velocity vector? It changes. What should we say here?
Some of all the velocity vectors as delta t.
Well, as delta t approaches 0, we expect, well, we don't do any sum here, right? When we talk about the height, we don't add those heights. What we say is that if the delta x is short, then what? Then the height will be either this one or that one. They are not the same, but what?
As delta x approaches 0, they get closer.
That they get closer. Can we expect the same here? As we make delta t go to 0, this vector, velocity vector at this point, is going to be closer to that vector, velocity at the endpoint. Does it really happen? Is that what we should expect? Because this is out of mathematics. This is physics. If this doesn't happen, integration is useless. You will not be able to make one of the steps in the integration process. But if you believe this happens, then yes, integration is useful. So, I mean, this is not just a couple of Mickey Mouse steps and you run through them and you forget about them. Right? You really have to understand why is it that in your problem additivity happens, and why is it in your problem that differentiability happens? And what does it mean for that application that you're working with? And then once you check that, yes, you have both, well, then you go through these steps, describe what linear case is, and step by step come to the integral, and then you integrate.